Good morning, everybody. Thank you for joining the March US Map webinar. We're just going to wait a half minute for people to hop online before we get started. If you're just joining us, we're going to get started in just a second here. All right, it looks like we got a lot of people on, some more trickling in. I'll start with housekeeping. My name is Harrison Dreves. I'm on the communications staff at the National Renewable Energy Lab. I'll be running the technical portion of today's webinar. So if you're having any issues, I'm the one to get in touch with. And I've just got a few quick housekeeping items before we dive into the presentation. Just a reminder on this Zoom webinar, everyone is muted. We've got too many people for everyone to unmute, unfortunately. There's two options for audio. Most people go with their computer audio, works great 98% of the time. If you're having one of those 2% kind of days, phone audio is always an option. You can either click the audio button in the bottom left corner of your screen to switch, or you can just leave the webinar, rejoin, and choose that phone call option when you join. And the phone is a good backup for weird internet days. If you're having technical issues with your audio or otherwise, message host using the chat panel. And let me turn that on so all of you can talk to us. I'll be watching that and I'll do my best to assist you with your technical issues. We are also going to be recording today's webinar as soon as I'm done with this housekeeping. So you'll be able to go back and watch it later on YouTube. We're going to do Q&A at the end of the webinar. You can submit at any point during the webinar. So if a question pops into your mind, go ahead and put it in. Use the Q&A tab for that. So the chat panel, single speech bubble, that's for technical issues. The Q&A panel, 2 speech bubbles, that's for questions for our presenter. And we're going to answer as many of those questions as possible at the end of the webinar. I'll also turn on upvoting on that Q&A tab. So if you see a question that you would have asked, but someone else already asked it, just give it an upvote and that'll let us know, hey, a lot of people want to hear the answer to that. All right, with that, I will hand it over to Joe Barry to introduce today's presentation. Joe?
Yep, hello everybody. It's a pleasure to welcome everybody back to the US Map webinars. We have a reasonable slate of webinars that'll happen throughout the spring, so keep an eye out for that. But with that said, it's a pleasure to introduce today one of the newest members of our technical staff, Ross Kerner. You can see the title of the presentation there. Ross was just recently added to our staff, but has spent quite a bit of time at NREL. He got his undergraduate degree at the University of Minnesota with Russ Holmes in material science with a minor in chemistry before matriculating to Princeton, where he worked with Barry Rand. And he graduated, I guess it was in 2019, if memory serves, but spent about the last year of that time actually on a project that was between NREL and Princeton at the time, out at NREL before joining NREL as a director's fellow postdoc, where he's been until very, very recently. So that's Ross in a nutshell, but I don't want to eat into his time. So I'm going to turn it straight over to him and let him tell you about some of the work that we've been doing.
Thanks, Joe. Yeah, today I'll be talking a lot about perovskite solution processing and mainly on this topic of the intermediates and their role in film formation. And I guess I'm not speaking to you as a super deep expert in this area, but more as a Joe and Laura told me to tell me what they can learn about intermediates. And so I delved into the literature and did some of my own studies. And so I'm going to talk to you, navigating it as kind of more of an average perovskite researcher and what I learned, and hopefully that's helpful. So I'll first summarize some of the activities at NREL in terms of the in situ space. Is my pointer moving? It froze on my screen.
It's currently frozen on like the graph in the upper right.
Okay, well, I'm going to talk about that first anyway. Yeah, so in the past, NREL or our collaborators have done some work on in situ annealing steps, so the crystallization, the transformation from the intermediates to the perovskite phase. What I've been doing a lot recently in the past 3 years is looking at the solution properties, so chemistry that occurs in the solution and the speciation in solution. A lot of open questions about that. And then sort of a new activity, there we go. New activity is doing in situ studies on the intermediates themselves at NREL. So I'm going to talk a lot about lead halide solution processing. Some acronyms, if you're not familiar with them, that I'll use a lot are DMF for N,N-dimethylformamide, DMSO for dimethyl sulfoxide, MA for methylammonium, FA for formamidinium. So really, solution processing challenges come down to two main things, I think. The main priority is getting a conformal film. If you can get a conformal film, you can probably get about 16% devices. This is kind of the defect tolerance limit. Like as long as you get a film down, you can get in the teens. And then after you've gone through all that and can control your films that well, then you can start asking how to control the phases, the impurity phases, how to properly convert to perovskite, the exact defects, and surfaces and interfaces as well. So I like to kind of take a step back sometimes and look at the history of things. I've been in the perovskite field since 2013, and I realize now that there are lots of people just entering the field and don't fully know, where we came from and what our struggles were in the early days. So the first perovskite solar cell was around 2009. And when I started my PhD in the years before that, I think really the two-step recipes dominated. That's what I started out doing. And then there were also some kind of odd 3-to-1 one-step recipes that gave decent results, decent films, but they were pretty hard to control. And that's really because when we tried to do the 1-to-1 one-step, and that means you just have, say, MAPI or FAPBI3 in solution and nothing else. When you spun coat, you got films like this, extremely rough, many pinholes through film, and you just couldn't make a working device. The two-step, just in case you haven't seen it, is you first coat lead iodide from DMF on your substrate. You get some solvated lead iodide. Usually we annealed or dried this. And then we spun coat MAI or FAI from IPA on top of the lead iodide, and then annealed that to convert to the perovskite. Then around 2014, the first solvent quench was demonstrated, and that allowed all of us to transition to the 1-to-1 one-step and get full coverage films. And the first PCE was 16%, and now we've pushed that past 25, I believe. But I want to point out that kind of in the end of this era, people were starting to look at doing the MAI IPA on the solvated lead iodide film. And I think that was maybe not the first, but one of a really good major success in terms of leveraging a known solvated film. So that occurred around here. And on the next slide, I have a way more busy timeline because this is a result of my kind of deep dive into the literature. So here's our two-step era. And then the solvent quench was introduced, but as I mentioned at the end, people started doing their two-step on the solvated film. So people actually started identifying the exact intermediate phases. And that's kind of how I broke up this timeline into intermediate phase identification and then in situ studies. And then there were a few years where the in situ studies lagged behind us identifying the exact structure of these intermediate phases. And now there's kind of an explosion of all kinds of phases databased and many, many more in situ phases. I should probably have a huge density of stars out at this end. But that's kind of how we got to this place that we're at now. First, we were doing lead iodide solvates, and people figured out how to do that. And then the one-step came along, and now the number of phases and intermediates really exploded. So what does metal halide perovskite solution processing look like? Depending on your recipe, and I'm sure most of you have seen this, but I just want to go over it in case anyone hasn't. But depending on the recipe and the pre and post quenching of your films, you'll see different colors. Right, so we start with a yellow ink. They're almost always yellow, but then when you do your coating, you'll get various yellows, almost transparent. Some of them are almost red. I have seen deep red ones too. Some of them are mixed brown, yellow, or brown. and then you anneal those to your final perovskite film. And the reason that we need a quench is because of the solution chemistry and the solvate chemistry, these are constantly evolving over time. So you kind of have to rip out the solvent really quick and try to get it into this metastable state that you can handle for a few minutes and put on the hot plate. But that's still evolving. And by evolving, really what's happening is the intermediate crystals are growing and growing. And if you let it get too crystalline, it opens up gaps in your film and makes a lot of surface roughness. And I think we also all appreciate that these are sensitive to myriad parameters, including environmental conditions and things like that. And so there's a art in perovskite processing. A lot of people kind of have an on-the-fly tuning strategy to get their conditions right. And they can just kind of look by eye, or maybe they have so much experience they know from other SEM like what things look like and what they need to tune to get a good film. I think in my experience, the base recipe is really what determines the intermediates. And the quench timing and things like that are more what determines the morphology. Because I haven't really personally seen huge impacts on the intermediate phases due to, say, drying rate or the substrate that you choose. But that's still a possibility that we could see brand new intermediate phases. Just telling you what my personal experience has been. So in this seminar, I think our main goal is to take what we've learned at NREL during our kind of entrance to this field and tell everybody about it and what is known about in situ studies already. And so I'm going to focus this talk on FA-based perovskites solely because they're the most relevant from device stability standpoint. I'm also going to limit the scope to DMF, DMSO, since there's a huge amount of literature, in situ literature on these phases, and not quite so much on other solvent systems. So maybe I'm opening myself up for questions about those at the end. But really, my goal is to talk about it in a way that can be applied by any worker. And I really hope that we can get some insight into these phases, or at least picture what's going on microscopically without the need for advanced characterization tools. Some of the questions or conclusions that you'll see at the end are, we should consider what the stoichiometry is of our expected intermediate. It seems huge to me. Something I've noticed going through this is that solvents are not as strongly coordinating to lead as we might have previously thought. I always thought DMSO is super strongly coordinating to lead. Now my perspective is kind of more like it does, but I don't know if I want to use the word strong. Another thing that I kind of held as a given going throughout my career up until this point is that bromide-rich phases, bromide is less soluble, so bromide-rich phases should crystallize first during coating. And now I've seen lots of data that point to the exact opposite of that. And the kind of a concept that I hold now is that Fa and Ma cations are dressed by solvents in solution, and cesium is naked. And I think of cesium more as a processing additive after these 2 years in the in situ intermediate project. And it incorporates into the perovskite, which is great. But really, it seems like its main impact is on crystallization. And then something that's super practical is that if you see orange and red intermediates, you might expect or anticipate a high density of twin boundary defects in your perovskite. And you'll see why after I go through the literature review. So before I do the kind of the distilled literature, I want to talk about the two main categories of studies that people use to look at intermediates. And this is the first type, which I alluded to, where people will grow halidoplumbate crystals. Typically they're aiming to grow some solvated intermediate. And they do this slowly by, say, anti-solvent vapor infusion, or they drop cast it, and it dries slowly. And then you can fish these crystals out with a little nylon loop. And then you determine their structure by single crystal XRD. And I consider this more of a slow growth thermodynamic. You can grow a ton of different phases this way, but we really need to be careful how to interpret the relevance of these. And we really need to verify with in situ studies that they're relevant for our process. And that's where the second type of study comes in, where you actually do the in situ GWAX or XRD during the film formation. You know, hopefully it's similar-ish to your process, but often it's not exactly the same conditions as your spin coating process. But these are kinetic, and they identify the exact intermediates that precede the perovskite formation. So it's really the kind of the combination of these two studies that give us a really good insight into what's going on. And just to point out the characteristics of these in situ GWAX studies is often in the very beginning, you see broad diffuse peaks, kind of a peak, I guess. Oh, let's call it a feature. And this has been called a gel-like character in the film. And then after that, from this, I don't know, kind of barely structured gel, you see these crystalline halidoplumbate intermediates start to nucleate and grow. And I think another feature, if you stare at enough of these papers, is that the optimal quench timing is almost always like right as these phases are starting to crystallize. So you don't want to let these intermediate crystals get too big. And I also want to say, if you're interested in these types of studies, I think you should look at Rama Massian, Eva Unger, and Ana Flavia Noguera. They've done a ton of work in this field. And before we get into the real weeds, I just want to show some types of intermediate structures, two different motifs. So this is a really common one. It's two DMF molecules, and then the chemical formula is Ma2 Pb3I8. I've been referring to this as the Pb3I8 phase. And it's this crystal where these ribbons are coming in and out of the screen. And these ribbons, they look like a small ribbon of lead iodide terminated by MA-H bonding, and the Ma is solvated by DMF. One notable thing about this is that this is not the right stoichiometry for your perovskite. So if you have a huge domain of this and you try to convert it to perovskite, you're going to see a ton of lead iodide precipitate out. The next one is one that, you know, is way more commonly talked about. This is the 2H FAPBI3 phase. It used to be called delta all the time, and now people are shifting to the 2H for hexagonal packing terminology. And I think the main driver for that is because there's also other delta phases that don't share any resemblance to this structure. So 2H is just kind of an added specificity to this type of structure. And this is composed of these 1D chains of face-sharing lead iodide octahedra. So the longer chain looks like this, and then they pack together in a crystal like this, where these are coming in and out of the screen. The most notable part about this is that there are no solvents in this structure. So this is an intermediate that's not solvated. And it is the right stoichiometry to get the perovskite. It just takes a lot of temperature to convert. So here we come to 5 papers that really helped me understand this field. And after you look at them, you kind of think, you know, instead of intermediates are really complex and I don't know what I might learn from them, you say, oh, wow, some people actually have a pretty clear picture of at least certain systems, solvent and compositions. The first one is this 4-mamidinium halidoplumbate intermediates paper by Alexei Tarasov group. Tarasov group was one of 2 or 3 that databased a ton of these types of structures. And they do the thermodynamic growth and the isolate large crystals, and they found a variety of solvated FAPBI3 phases, some of them shown here. And I show this paper because it's kind of the counterexample, or it gets to what I was talking about before. Which of these are relevant? Have any of them ever been seen in situ studies? And I haven't found a ton of great examples, but I'm sure that there are some out there, some processes that do leverage these types. The second paper is by Nazirudin group. It's called The Many Faces of Mixed Ion Perovskites. I was shocked when I found this paper. It was in 2017. Like, I should have known about this during grad school. And it basically outlines exactly what people started to see and have been seeing in situ studies. And so they do the thermodynamic growth as well. And so here is the 3C. This is the cubic perovskite structure. Here's the 2H or delta phase that I was showing. And they found that when they started adding more and more bromide to their FA-PBX3 ink, they isolated this 4H phase, and then they were also able to isolate this 6H phase. And these colors are chosen intentionally because these are the colors of the materials, as I'll show on the next slide. Yeah, so the 4H is yellow, 6H starts to become orange, and then since then, actually the next paper will show 8H has been found, and so that is responsible for the red. The 3C is brown, and it's really amazing that they were able to do this in solution growing large crystals, but adding cesium was shown to prevent the 4H and 6H phases. So when they added just a few percent cesium, you basically couldn't grow 4H and 6H. And then there's also discussion of this 3R phase for rhombohedral, I believe. And they kind of talk about it as essentially a highly twinned or strained polymorph of the cubic perovskite phase. And it looks so similar in XRD that you can't really distinguish them on a laboratory scale instrument. The other notable thing about this phase is that if you do fall into this phase during your intermediate formation, it's really hard to convert that to perovskite. Often it goes back to the 3R. You have to apply quite a high temperature. And we don't want to apply high temperature because then our organics start decomposing. So they pretty much outlined all these different phases and said, really try hard to avoid this one. You should be able to do it by adding a bit of cesium. So here I'm kind of showing the 6H intermediate right here. And if you block out the phase sharing components of this crystal, this is just perovskite, right? But then you show the whole thing and you see that it's twinned via a phase sharing, like a 2D layer of phase sharing. So I think this is a really cool, kind of opened my eyes to the propensity of perovskites to form these types of defects and maybe even where they originate from. And I have questions around, whether these induce strain and things like that. But you could also imagine that, I'll say that the angle is 111. I'll show this later in some TEM, but it's good to note now the angle between these two at the twin boundary is 111 degrees. And you can also ask, say, is this kind of another form of dimensional confinement? Can this be regarded as kind of a 2D phase perovskite, but very different from the Ruddleston Popper or the Dion Jacobson that we're more familiar with? I think the last Easter egg in this paper is that they also observed the DMSO intermediate. And by DMSO intermediate, they're referring to the PB3I8 phase. That's what I call it. And they isolate crystals of these from their growth vessels, and they do EDX on them. And what I thought is super cool is that the 2H phase is pure iodide. There's not really any bromide signal, but the DMSO intermediate can incorporate some bromide they found. And I think it's an open question as to how much it can incorporate. So this 2H phase is pure iodide. PB3X8 can incorporate both. And this one can't incorporate it because as soon as you insert as soon as you start inserting bromide, that's when it just induces the 4H, 6H phases. I really liked this paper as well because they're able to isolate the 8H. So this opens up, it's basically a continuous transition from 2H, any number up to what you might consider just a highly twinned cubic phase. And they also concluded that 4H and 6H are bromide rich because it's when the bromide inserts. And I think they hypothesize it inserts into these corner sharing layers right here. And then that's what induces the structural transition. Paper 4 I include because they do the in situ. I think there might be some before it, but this is one of the earlier ones where they do in situ measurements, basically confirming papers 3 and 4. And they come to the same conclusion and prove it in a kinetic study that cesium suppresses. It basically skips over the 4H and 6H phases. So it's a little small, but right here is the 2H phase. Here's the DMSO intermediate. And they add 1% cesium and then do their solvent quench and see a little bit of perovskite nucleate. They add 3% cesium, and there's still the 2H phase that comes in first. And then it transitions to perovskite and 5% cesium, which is kind of their critical number, almost completely avoids the 2H even. But you see there are no 4H and 6H phases, which show up kind of in the middle here. And then paper 5 kind of goes beyond DMF, DMSO. And this one is by Nanfeng Zheng group, who also are kind of leaders in this field. They were the second group whose database, almost uncountable number of intermediate phases in the crystal database. But what they've come to most recently is this realization that the solvent is kind of in a tug of war between solvating lead, which is kind of what we always think of, right? We had strongly coordinating solvents to lead to slow down crystallization. And it turns out that a lot of them actually H-bond to the A-site cation. So they outline this here, kind of a donor number as a measure of coordination strength to lead. And then that Camlet-Taft parameter is sort of a measure of H-bonding strength. And the really nice part of what they've showed is that the solvent can drastically change the thermodynamics to convert to perovskite. And that's kind of an advantage of using solvent processing, among others. But in my mind, this chemically modifying the transition barriers or the temperatures you need to convert to perovskite is huge. And some other processes don't really take a leverage of that. So the delta FAPBI3, I think some of us may know, you have to go above 150 to convert to perovskite. If you've got DMSO in the film, it's forms some sort of intermediate and it lowers the conversion temperature to 100. FA and NMP seem to have some magical synergy where it goes even lower and you can convert to perovskite before 100 degrees C. So the important takeaways from really the literature search and kind of historically looking perspectives are that the intermediates dictate the energy transition to the cubic perovskite phase. I don't know if we know how to precisely manipulate that yet. It's something we're very interested in looking into more in the future. And then some of the kind of just overarching takeaways is that, keep in mind that intermediates can contain solvents or not. If they are solvated, it can bond to the MA or the FA more preferably than the lead. I actually don't know if I've ever seen decent proof of a lead solvated intermediate in any in situ literature I've looked at or in any of my own measurements of in situ. So yeah, this is really, I would pay attention to what Nanfeng Zheng does in the future on this type of stuff. If you have MA in your system, it seems to greatly increase the PB3I8 tendency to form, which can be mixed halides, but it's not the right stoichiometry for perovskite. And then you can have the 2H non-solvated, and we're going to look at the 6H, 8H, and cubic further. And just a reminder that, so delta cesium PBI3 is one of these delta phases, but it's orthorhombic and doesn't have any of the same bonding motifs. So I encourage you to help us adopt the 2H FAPBI3 terminology. And what I'll show you in the next couple slides, but I've already showed you the first piece of literature on this, is that these FA-cesium lead iodide bromide perovskites from DMSO show crystalline intermediates that are not solvates, which I found somewhat counterintuitive and surprising, but the evidence is overwhelming. So here is where I'll dive into data kind of confirming this. These are our preliminary measurements, basically getting our feet wet in the field, and I'll thank the Mike Toney group at Sea Boulder for helping take most of these measurements. So just as a control, let's look at MAPI from DMF just to make sure we know what we're doing. So as we spin coat, at some point we get these peaks to emerge, and I can go into Nanfeng Zheng's SIF and simulate the XRD, and it looks like almost a perfect match. So we know what we're doing, we're spin coating properly. And then we kind of move towards more state-of-the-art compositions, because at NREL, we use a ton of FA-cesium-based stuff, sometimes with iodide, sometimes without. Chloride additives are something that hasn't been reported a ton yet in situ literature. Now they are quite common, but back when we did this, there wasn't much, so we thought this would be a nice thing to look at. Let's do the base recipes with and without chloride additives. So FAPBI3 from DMF DMSO. All you see is the non-solvated 2H phase form. Add a little bit of cesium. Doesn't really change much, but the kinetics are delayed by a long time. We add even more cesium. Okay, now we see something. Now we see something that might match well to perovskite. Yep, that's about one. So you definitely see the 2H phase nucleate first, and then something that might be perovskite afterwards, but you have to add in a ton of cesium. And then here's a cesium-free control, and it also served as our sample with bromide in it. This is a bit unexpected for me, given the literature search that I did. So all you see is the 2H FAPBI3 form, and that's it. I really expected to see some 4H or 6H. But I do see one sample, so you'll see it in one sample, so you get to see what that looks like. And now we move on to with the chloride additive. Start with our control of just FAPBI3 with chloride additive. We see a new phase that nucleates along with the 2H phase. Chloride also helps to slow the kinetics down a lot. We add our 5% cesium, and really it looks like the same thing, a little bit slower kinetics. And then with 15% cesium and the chloride additive, our kinetics are extremely slow. And we see the perovskite and the 2H nucleate at the same time, essentially. And finally, with our cesium-free control, we add chloride, which maybe I just didn't have enough bromide in this composition, and so the chloride may help it act a bit more like bromide. Now we see what we expect. Consistent with the papers, the very first thing to nucleate is the 2H pure iodide phase, and then you get these peaks here and slightly higher in Q than the 2H phase, and these are the 4 and 6H phases. And then perovskite comes in last. So all of our results match, basically, the key papers that have been published in this field on DMF, DMSO. Now we'll kind of transition to a bit more speculative type, kind of questioning, what's important? What do we think might be fun to look at in the future? And so if it's the solvent, if the solvents aren't really participating in the intermediates directly, like within the structure, then what types of interactions do dictate the intermediate phase? And after talking a long time with Jeff Schwartz, a chemist, he kind of concluded it might be due to H bonding and the effective size of the cations. And what I mean by that, what he really means by that, is that very small cations are very polarizable. So they actually have a huge solvation shell. So in solution, they look massive. And then things like cesium are so, in his words, fluffy that they don't care to coordinate to anything. So in this sense, the cesium is not expected to be solvated. And if Fa and Ma are really solvated, kind of strongly H bonded to a solvent, then cesium is by far the smallest cation and can like most closely approach those weird iodo-plumbate intermediate polymers, as they're forming. And the second kind of speculative or like forward-looking questions are, if our intermediates have a high propensity to form phase-sharing twinning boundaries, basically, then are these the origin of 2D defects in perovskites? And then what might that effect have on the optoelectronic properties? So fairly recently, and going back a few years, there's been some amazing advances in how people can do TEM on these perovskites, and we're starting to actually get direct images of defects, which is super cool. This TEM was done by Yan Zhou. And in this figure particularly, he sees this twin boundary exactly with the angle of 111 degrees. So that's probably just a single twin face sharing, and then he sees other inclusions that could be, if you zoomed in on this area, that's basically like a 4H type defect, just one layer of two face sharing, two twin boundaries really close together. Laura Hertz, I also want to say, has done a ton of really good TEM and seen a lot of these phases like here, and I think this is kind of a twin boundary. And Joanne Etheridge also has done a lot of this. And this was one I found while I was making this presentation, is that people have actually done DFT to simulate, what are the optoelectronic properties or possibly phase stability properties. And this was done so far ahead of its time, actually, in 2018. I'm only just now catching up and kind of uncovering how far back people have looked at these. So those TEM prove that twin boundaries are real in perovskites. And Laura Hertz has kind of taken this to the next step, where she's observed the effects with more accessible techniques. So what's shown on the right is a Fa-based perovskite film, and she starts doing low temperature UV vis, and these oscillations start appearing. And at MRS, she described as probably some kind of, dimensional confinement, possibly arising from these types of twin boundary defects. So the question is, how do they originate from the intermediates, or in what way are they related? And then what impacts do they have? And how can you characterize them with, accessible techniques? You can do low temperature UV vis much more easily than TEM, or definitely much easier than, say, in situ GWAX or synchrotron structure determination of a final film. And you could even go a step further and say, if I see red at any point in my intermediates in my perovskite film formation, should I expect a high density of twinning defects? Should I avoid that red and orange? Or what can I do to avoid that? And does it give me better perovskite material properties? That brings me basically to the end of my talk, the summary and the takeaways. Just to reiterate, the data in the literature is guiding our intuition and kind of correcting some of it. That, solvent coordination to lead may be important, but it's not a given, and it doesn't really determine the final intermediate structures that we get. And most of the time you see them DMF and DMSO H bonded, if they're solvating at all. The bromide-rich phases crystallizing first from solution is also not a given. I'm sure there are many examples when and conditions where this does happen, but seems in our state-of-the-art perovskite compositions, it's the 2H pure iodide phase that forms first. And then, thinking forward about how to manipulate your solutions, the Fa and the Ma are dressed by solvents where the cesium is naked. And that's where I was saying that, I almost view cesium just as a processing additive first and a constituent of the perovskite second. And then the orange, as I said, the orange and red intermediate, 6H, 4H, and then 3R is brown, but could be kind of a defective trap. Can be identified by eye. So, as you're doing these things, you can kind of picture what might be happening on an atomistic or microscopic level. And it's an open question about the twin boundary defects, but I think an interesting one. So yeah, my main point is pay attention to the intermediate colors. If you're working on systems that are well studied, you can pretty much know the structure without having to measure them, just by being very diligent on your observables. And then, I'll leave you with one very last question with, what do you think, or what might we do to get the ideal intermediate or process? Maybe it's not even a solution process to make perfect FAPBi3 perovskites. Obviously, you can do FAPB bromide and stuff too, but just overall, what should we be doing to push beyond, okay, we can make conformal films, we can make really good devices. How do we push the semiconductor technology even further and minimize 2D and point defects? So with that, I'll wrap up and thank the various projects that have contributed even adjacently to this study, and everyone who has worked with me, and even people who have endured conversations with me about the very specifics about the chemistry of intermediates. And there are a few questions, it looks like, so
yeah, thank you so
give
much,
it back to
Ross.
Laura.
So virtual applause. I think it was a ton of information and a really nice summary of the literature. So I think we all thank you for reading the literature so thoroughly for all of us, and then telling us what you learned. It's certainly helpful, as well as sharing some new results. So the first question that we have is related to paper number 2. And in particular, what instrument you can use to distinguish between the 3R and the 3C phase if XRD cannot.
So it's been a while since I've read that paper in full, but I think what it is they did single crystal XRD for all the phases, and they're able to get a great fit.
Mm-hmm.
And then for the 3R, or kind of crappy 3C crystal, you can't get a good fit. So they kind of play with parameters, and then, they database it anyway. But any crystallographer would understand there's a caveat that, like, well, it was just a crappy fit, so it's probably highly twinned, like really crappy crystal.
Mm-hmm.
They hate twinning when you do single crystal XRD. That's what I've learned from my brief studies in that.
It makes the structure solution very difficult because you're assuming it's a single crystal, and in fact it is not. Cool. So the next one is about the absorption spectra you showed from Laura Hertz. And in particular, they're asking what the oscillations are at low temperature there. Can you comment on that?
Yeah, I don't know if it's been unambiguously confirmed, but if we make the analogy to the 2D phases of perovskites, or if you're familiar with the n equals 2, n equals 3, n equals 4 versus n equals 1, the band gaps or exciton energies slowly redshift. So basically, I think what you can infer from the data and what they kind of wrote without making any strong claims is that the twin boundaries determine a variety of n equals 2 to 4 to 6 within their film. But as soon as you get to n=10, the band gap in exciton is basically bulk. So I've seen lots of TEM of, say, twin boundaries about every 4 to 6 lead iodide corner sharing octahedra. And so if there's a variety of that in your film and you go to low temperature, you can start seeing those.
Okay. Great. So the next question is a little bit of a two-parter. So since these perovskites are printed on bottom contacts, it seems like the nanometer scale composition of these contacts has to play some role in controlling the solution chemistries and the formation of different polymorphs. However, they go on to say, or since nucleation starts at the ink-air interface, maybe not. So I think to summarize, how does the nucleation direction impact the way these intermediates form?
I think my answer would have to be the intermediates are maybe unrelated to those types of disorder and non-idealities at interfaces. That really comes down more to, did you quench at the proper time? And did you get your solvent ratios right? Do you have to wait a few minutes before putting it on the hot plate, or does your recipe have to go directly on the hot plate? Yeah, I can't say much about the exact role of the intermediates there.
All right. Okay, so I think this is a good question. Is there a smoking gun paper that shows the importance of intermediates for the final perovskite, i.e. efficiency or stability?
Sorry, what was it?
Is there a smoking gun paper that shows the importance of intermediates for the final perovskite, i.e. kind of how it impacts the efficiency or the stability?
Nah, not that I know of.
Okay.
It's really hard to get your exact 25% recipe dialed at the beamline with modified spin coater conditions or blade coating in air or whatever we're kind of limited to.
So is it safe to say then that there's still work to be done to fully connect what we're learning at the beamline with these in situ studies and what we measure in terms of device performance and stability? I think there's fundamental things that we're learning, but there's not a direct correlation yet.
Yeah, I mean, absolutely. There's so much work to be done. I only was able to present on a small portion of DMF, DMSO, FA, cesium because, that's what probably at least 50% of the papers were on up till now. And, now I'm starting to see papers come out on 2-methoxyethanol inks and things like that. And there's literally a handful of them. So, eagerly awaiting what people will show next.
Great. And then I think moving into a slightly different space, in vacuum deposited perovskites, there are no intermediates. Doesn't matter.
Can you repeat that one again too?
In vacuum deposited perovskites, there are no intermediates. Doesn't matter.
What do you mean there are no intermediates? Oh, vacuum deposited perovskites. Sorry,
Okay.
I was thinking vacuum quenched.
Nope, vacuum deposited.
I don't know if that's a given either. I mean, I've seen people convert their cesium, lead, iodide, bromide from yellow to red to black as well. I think they're intermediate still. I think they currently don't take advantage of solvents and solvation, but there's no reason that they can't either. Put your film down, get some weird intermediate in air. I don't know, anneal.
All right, so moving into sort of chemistry, stoichiometry question. Do you have any estimate to which extent the exact composition or off stoichiometric compositions, for example, PBI2 rich, influence the crystallization temperature or which intermediates will be formed? and how sensitive is this correlation?
So I'm pretty sure that the 15% recipe that I showed is highly lead iodide rich. So if you go back and compare my slides and say 5 versus 15%, that also includes, I think, a variation in lead iodide stoichiometry. I have to say I don't have a great sense of that. I'd have to go dig in the literature, see what's been done.
Okay, so now some insights into what you observe. This person says they work with rubidium, cesium, MAFA, PBIBR, perovskite, so the kitchen sink plus everything in their refrigerator. And I've noticed that the film turns black before turning gray right after annealing. The grayish perovskite yields a higher PC than the black phase. Have you ever observed such a transition? And they would appreciate any insights you have into that matter.
Yeah, I'll share that. I mean, I have this in my library somewhere. Cesium and rubidium work effectively the same way as an additive, skipping 2H, 4H, 6H. So that's kind of nice and interesting to me. In my device experience, the gray is mainly a roughness issue. So, you know, as long as you don't create pinholes when you evaporate or however you deposit your next contacts, like gray with good crystallinity and few pinholes should be great at light scattering and maybe boost your JSC a bit.
Great. I think we are about out of questions. So I'm going to put Joe and Yao on the spot and see if you guys have anything you wanted to ask Ross while we still have some time. While they're thinking, I guess, Ross,
I
what
can
do you
answer
think?
one more question just about highest device efficiency. I mean, I don't make devices, but I made the inks copying someone who makes regularly makes 23 to 25% for several of the compositions that I showed for our data.
So I was just hunting for my controls.
Yeah, same here.
I guess, Ross, for those who don't know, Ross has done some work also examining some of the precursor purity kind of questions. And I was curious if you could maybe comment on how some of that work couples to what you've basically talked about here today.
Well, I'll say the direct result is if you have the wrong impurities, your MA and FA will react. And MFA and bulky formamidiniums typically affect the 2H phase very strongly. And so it's more like the impurity changes the composition of your ink uncontrollably. I don't know if my assumption is that trace impurities don't hugely affect the intermediate that you'll see, but defects that are harder to see will be affected.
I guess that would be another thing that, you know, is maybe worth commenting on is the question, right? I mean, the question was kind of posed, well, what's the overall efficiency, right? I mean, things that we can see in XRD are at a very different level of kind of incorporation or inclusion in the context of the film relative to, say, you know, what somebody like me would imagine for semiconductors.
Oh yeah, I mean, XRD is bulk. So like,
yeah,
you could have two perovskites with orders of magnitude different twin boundary defects, and in your XRD, they might not be distinguishable at all.
Mm-hmm.
Go ahead, yeah, if you'd like, or I can continue on.
I was wondering if Ross could comment a bit on knowing some of what you've learned here, what would be good sort of tools that you could put on a production line when people listening in the audience are commercializing these technologies? I mean, should we put XRD tools on our lines, or are there other methods, this optical methods and that sort of stuff?
I'm partial to like what Jesse and Axel have been doing, and Amy with like a optical interferometer.
Mhm.
Because if you're waiting for an XRD peak to form, you probably already past the point where you should have quenched.
So Ross, we've got a pretty large and diverse audience here who probably have no idea who Axel and Jesse are actually referring
Yeah.
to. So can you unvague that statement for the
Unvague.
audience?
Sure. Axel Palmstrom is a staff scientist here who's looking into environmental controls and evaporation rate, calibration curves. Just what is the evaporation rate effect and how do we monitor it? Jesse Starger, I hope I pronounced his name right, was a Drexel student intern over the past summer who carried out most of the work. Amy is a graduate student at Colorado School of Mines, co-advised by Axel, who also was working closely with Jesse.
Great. Yeah, maybe you'd set
Sounds
us
like you
up
just
with a good idea for another webinar in the future.
Yeah,
I think
exactly.
that does lead into a really good idea. So I
Mhm.
think with that, Ross, any final thoughts you want to share with the audience before we let folks go?
Just that, yeah, I hope this helps you visualize things better, and I'm sure you're working on newer stuff, and we'd be happy to chat more about what might be happening in your system that's more of interest to you, and even do work in the future.
Great. Well, thanks, Ross. And thanks everyone for joining us. We do have a number of webinars lined up now over the next couple months after a little bit of a break with the US MAP webinars. So please keep an eye on the website and get signed up and look for those details. Joe, off the top of your head, do you remember who is next month?
I am not sure. I know that the next month is April.
Okay. Step one correct. So I think with that, check the website and look for emails from us on new stuff. And Ross, thank you very much. I've seen some of this before, but every time I just really appreciate the distillation of a lot of information. It's really helpful. So
yeah,
thanks.
Literature and perovskites needs to be a team effort.
Yeah, totally.
Cool.
Yeah, thank you all for coming.
Thank you, Ross.
Bye.